Okay. All right, I'm trying to get the screen sharing to happen. Okay. Okay, I think we're working now. Took a while for it to pick up. So let's go from current slide. And this is Math 238. It's Monday the 30th of March 2020, and it's 2:30 plus in the afternoon. It's supposed to be the differential equations class 238, and so far I can't tell that any students have logged in yet. I know I'm here and I'm the only one so far. So I guess what we'll do is just pick up from where we left off last time and go from here, and as soon as some students show up, then I'll make any announcements. Is someone here?
Can you hear me?
Yes. And who is this? This sounds like Vince, is it?
Yes, it's me.
Okay. Got you. And I guess Keyston isn't here yet? Can you tell?
Let me see, for instance. No, he's not here.
Yeah, I can't see any. I can hear you, but I can't see any indication you're here. But I can hear you, so I know you're there. And Keyston, I hope will be in later. Now, Peyton Gunter, I haven't seen that he's shown up on the roll again. He was going to go by and talk with him, but that's about the time the school closed, so I don't know if he ever got back in the class or not. Is Peyton here?
No, it's me here for right now.
Okay, and so this is still just Vince, right? Vince.
Yes.
Okay. All right. Well, I was just going to say I'll put off announcements until someone shows up, but since you've shown up, I'm going to make it. I'm guessing you... Say again?
It was a little weird with like the message thing. Like it doesn't like properly notify us. Like it'll like I knew because I got an email from you. I got it like sent to where it sends me an email whenever you leave a message. But then like sometimes if you go like you gotta actually go in there and click it. Or because like if you log into your Blackboard and you like open it too fast, your messages from all of your teachers might just disappear. And then like you gotta go and physically click. Because I was trying to see, like, I was like, I know he had to put the password on here and stuff. So maybe that's what it was.
Okay, and this is still Vincent, right?
Yeah.
Okay, right. Is Keyston here yet?
No.
No.
I'll let you know when I see him. You know.
Okay, right. For some reason, I'm not seeing anything but a white screen. Do you see the white screen?
Yeah, I see the white screen.
Okay, good. Okay. Now this is the thing. Okay. By the way, I found out I had, I guess, been saying that I was sending an announcement. And I thought what the new Blackboard Ultra was calling, oh, I can't remember what term they used for it, messages. I thought those were the announcements. But I found out there is a separate thing they call announcement. I'm doing everything through messaging. So that's what you should go for to find the stuff for me, the passcodes and all that kind of stuff, is the message. On my Blackboard, when I get in the course, there's a few sort of icons across the top, and one of them looks like an envelope, and that's the one that says messages. And that's what you open, and that's where I'll be sending, the announcements about the classes. That's where I'll be sending your tests. That's where I'll be sending everything. Is through messages, right? I've been calling it announcements. I thought those were the same, but a student told me this morning, no, they're not, because he had been looking under announcements for my codes, and he couldn't find them. He just had to look around until he found something. He said, I found them under messages. I said, was that the same as announcements? He said, nope. I said, oops. Okay. So that may be what.
Okay, yeah, I see it now. Yeah, it's under messages.
Okay. All righty. Sorry about the confusion. I thought those were the announcements. This new Blackboard Ultra is anything but obvious. Okay.
The last time when we had class on the 18th, it did come to our announcements. So,
It did.
yeah, it's like I'm looking at it. It was literally under our announcements, but this one went under our messages.
Wow. Okay. Maybe I was doing something differently, but you see, those I had to do right before class because I didn't have the paid version. So now I have the paid version, so I can do them as as needed, ahead of time and all that kind of stuff. So that's where they'll come through the messages, and that's where I'll look for your stuff too. Hint, hint. Okay. From this, one of my best classes ever, of course, I have received 0 papers as far as research papers. Please don't forget those. And but I have received both of your first test, and one of you turned in your second test, and thanks for that. But that's okay. Let's talk first about the research papers. If you do your paper in Word, then you can just send me either by email or a message on Blackboard, attach your Word document to the email or to the message on Blackboard, and send your research paper that way. Okay. If and you've already turned in your second test also, but when I give you your third test, then I'll send it through the message, and then when you're ready to turn it in, what you can do with that one, since you probably won't have that in Word, what you'll probably want to do with that is either scan it if you have a scanner or access to a scanner, but if you don't, you can take a picture with your smartphone, and I think I've gotten everything that I know of that people have sent. Now, my old laptop, not the one that's in my office now, but the one before that, it wouldn't take a JPEG file and some of the other picture files, but my laptop here does. As far as I know, it takes them all, so you can either scan it and send it to me, either by email or through Blackboard, or you can take a picture and send that either by email or Blackboard. I've gotten them both ways from students in my other classes, so either way will work. The easier way to do your research paper, though, is do it in Word and then send me the Word file, and that'll be very easy on both ends. And all right. Any questions that way? No. Okay. The other sort of major announcement, and so far all students have known this, it sounded like already, or at least if they didn't know, they didn't say they didn't know. Evidently, I don't think anything's come from the college yet, or maybe it has, but this decision was made over the weekend sometime that we are not going back to campus this spring, period. And that's not a big surprise at all. I've been saying that all along. This thing is still getting worse. The numbers are increasing almost exponentially, and soon we're going to see the deaths start increasing almost exponentially. So we're far from over. No matter what anyone says about Easter or anything else, April's going to be a terrible month. Hopefully the worst month, that we don't continue this in May, but it's still going to be bad. So the school is not opening back. I mean, we're open, but we're not on campus for any of the rest of the spring. And there was a faculty meeting this morning at 11, and perhaps the president made some further announcement there. I was in class then. I'll go to that same session at 6 o'clock. And I don't know if they're going to do the whole meeting over or just have a recording of the meeting. But anyway, I'll find out if there are any new announcements since then. I'm anticipating some, but I haven't heard it officially, so I don't want to go any further. But evidently, the other students had heard we are not, and I had heard too, we're not coming back to campus this spring. Now, I think the campus is still technically open. Security is there, and a few administrators or other people are coming and going, picking up things that they need, but people are trying to stay 6 feet apart and not linger very long there. Okay, so if you do need something on campus, locate and contact campus security first, let them know exactly when you're going to be there, what you need. They'll make sure you get there. Don't expect any offices to be open unless you know someone has told you they're going to be there too, because you're not going to get any. Most of the offices are going to be closed. I've heard that a few people are there just taking care of things they can't take care at home, but by and large, campus is closed, except someone is there, security specifically. All right, any questions? Okay. So let's pick up where we left off last time. We were in Chapter 4, Higher Order Differential Equations, Section 4.1. We hopefully will finish today. Maybe not, but hopefully will. Man, this is a long section, okay? And this is Preliminary Theory, Linear Equations. So we're looking at linear equations now for higher order differential equations. So we're on the middle of page 124. Solutions of differential equations. All right. Now we have been talking about this. Some of the things we've talked about, that if you have a solution, and if you have more than one solution, a whole number of solutions, then any linear combination of those solutions will also be a solution. That was theorem 4.1.2 that we did last time. And we talked about linear independence and dependence last time. And that was where we sort of left off. So now let's get back to looking at solutions of differential equations. Middle of page 124. We're primarily interested in linearly independent functions, or as they say more to the point, linearly independent solutions of a linear differential equation. Okay? Now, it says, although we could go to the definition and have the n solutions, y1 through yn, a homogeneous linear nth order differential equation, linearly independent, can be settled somewhat mechanically by using a determinant. And I'm trying to remember, both you and Keyston were in linear algebra last term, right?
Yes.
I thought so. Okay. So this is nothing new for you. So here is one way to determine if that set of functions is linearly independent. So let's say you have n functions. Let me get my pen set up. Okay, f sub 1, f sub 2, f sub 3. My pen is really messing up today. F sub 3, dot, 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 all the way up to and including. The pen is not writing when it's supposed to. And I can't, okay, and then it writes 3 times. Okay, up to f sub n. There's n linear functions that are solutions. Each of those functions supposedly is a solution for your differential equation. Okay, and we don't even need to be talking about differential equations now. Let's just say they're n functions. Now, each of these functions possesses, and my pen's not writing at all, and I don't know why. The last time this happened to me, I would get a message every now and then saying my signal was weak. It doesn't seem to make any sense, because the pen should be writing on the ionizing thing whether its signal's weak or not. I don't know, so I don't know if they're connected. Let me see if I can get it to write again. These possess, okay, now it's writing better. If I slow down, it seems like it works better. Possess at least, it's not writing, it's writing every other letter approximately. Okay, at least n minus 1 derivatives. Okay, these n functions, each of them possess at least n minus 1 derivatives. And that really came out poorly, didn't it? T. It's just not right. Derivatives. That's a V there. Okay. I'll stop. Okay. So, I don't know what's going on. I just got a blank screen. It says end of slideshow. Click. Oh, I know what happened. Okay. Sorry, I thought I was about to panic there. All right. Here is a thing called a Wronskian. Okay. Named after, I think he was a Polish philosopher and mathematician, Józef Maria Wronski, or something like that. Lived back about shortly after he was born during our revolution, 1778, and lived almost until the time of the war between the states, 1853. So that gives you a time frame. He came up with this concept. The Wronskian is based on these functions: f sub 1, f sub 2, f sub 3, ... Now, see, the pen writes some things, and some things it doesn't. Like the 3, it didn't write completely. Up to and including f sub n. Okay? And here's what it is. This Wronskian is the determinant. Remember that from linear algebra? If I could get the determinants. I mean, it's a real simple thing, just a vertical line. There we go. Okay? And here's what it's a determinant of. The first row is f sub 1, f sub 2, f sub 3, ... up to and including f sub n. First row are the functions. And the ... came out as one horizontal line. I don't know why. The second row is f prime of 1. It won't write. And I don't know why. Okay, f prime of 1, and that's not a double prime. It's just I kept trying to write f prime. There we go. Okay. F prime sub 2, f2 sub prime, f3 prime, ... up to f sub n prime. Third row, you might guess. What would you guess it would be? Yeah, double prime. Okay. And then f sub 2, double prime, f sub 3, double prime, ... up to f sub n, double prime. And it keeps going up. Now remember, you can only take determinants of square matrices. You have n functions here, so that's the number of columns is n. The number of rows has to be n. Well, the first row is the function, the second row is the first derivative, third derivative, second derivative, third derivative. So it goes up to the f sub 1 n minus 1. Okay? The n minus first derivative. Now you might ask yourself, is that the right number? Of course it is, because your first row is your zeroth derivative, just the function. So the first derivative, second derivative, there in the second, third, fourth rows. So the nth row would have the n minus first derivative of f1, the n minus first. It won't write. My pen will not write. Okay, n minus 1 first derivative of f2, the n minus 1 first derivative of f3, ... up to and including the n minus first derivative of fn. That determinant, okay? If you have n functions, doesn't have to be anything to do with differential equations. We're going to deal with if these are solutions to a differential equation. Then the first derivatives, the second derivatives, the third derivatives, up to the n minus first derivatives. Make a determinant of all those, write them in, and this is called the Wronskian of the function. Okay? So what? Okay? Well, here's what the next theorem says. I'm going to try to do this on the same page so it'll make more sense. So let's just suppose, and now my pen isn't even showing up where I put it down. Let y1, y2, y3, ... up to y sub n. Now, why they changed from f's to y's, I don't know. They represent the same thing. These are n solutions, and my pen is not writing. That was to be an S, that was an O, that was an L, and that was an N. N solutions of the... Now remember, I don't know if you remember what we were doing before. I know it's been a couple of weeks, long time passing, and you see the pen's writing some but not the other. We were dealing with linear differential equations. We're dealing with linear nth order differential equations, therefore the n there. But we're also dealing with homogeneous. And my pen is not writing. I'm spelling homogeneous and nothing is showing up. Let me try again. It will start writing and then stop and then start again. I'm going to abbreviate that next time. Linear nth order differential equation. I should have just done differential equation, DE, okay, on some interval I. Okay. Those are your n solutions, or are n solutions. This is supposed to be an of, and it doesn't look at all like an of. No, I don't know what that was supposed to be. Oh, that was n. Okay, sorry. It was so bad I couldn't even make out what it was. These are your n solutions. I can't get the pen to change. There we go. N solutions of the homogeneous linear nth order differential equation on I, and then it just changes wherever it wants to. Okay. This set of solutions is linearly independent I can't get the Y to write. There it goes, 3 times now. Linearly, it's just not independent. Okay. On that, goodness gracious. On the interval I, if and only if, these are important things, if and only if this Wronskian that I just talked about here, now we're using not f's but y. y1 is one function. If it would write, it won't write. It just quits right there. There's y1, y2, y3, ... up to and including y sub n. There's all those solutions. The Wronskian of all those and their derivatives is not, I hope you can almost fill in the thing, not equal to 0. Okay? For every it won't write. I don't know why it won't write. Every, there it writes everything at once. Every x in the interval. Okay. Whew. It was so hard to write. So here's what the deal is. If you have a bunch of functions that you know are solutions for a given differential equation, you have n of them. Now, n would be the most number of solutions you could have for an nth order differential equation, linear nth order differential equation. But you don't know if these are linearly independent or not. So get them, write down those n equations across the top, then the second line take the derivatives of those. Third line take the second derivative of those. Fourth line the third derivative. Yeah. And keep going until you get n minus 1 derivatives. That gives you an n by n matrix. Take its determinant. Now that is not an easy thing. Okay? But usually you don't have that many. Okay? So take the determinant. If that determinant is not 0 for any value of x, for any x in that interval I, then you have a linearly independent set. And you're happy. You're going to go with that. So we're going to show this on, they're not exactly examples, but they're mini examples, you might say. Okay? Now, it follows from the theory that I just wrote down that when those n solutions, you have those, and the Wronskian is either identically 0 or never 0 on the interval. Okay, those are the only two possibilities, right? Thus, we can show that the Wronskian not equals 0 for some x on that interval, then the solutions are linearly independent on that interval. Okay, so here, that to me was just a lot of double talk there, but let's say, here's a solution. Y sub 1 of x happens to be cosine of 2 log x divided by x cubed. Boy, what a function. Okay? Here's a second one. Y sub 2 of x. Boy, that's how that came out. That's really ugly. Is equal to sine of, see, the n didn't write completely, the s didn't write completely, the parentheses didn't write at all. 2 log x divided by x cubed. Okay. They claim that these two functions, y1 and y2, are solutions in the book they have and solutions, that's supposed to be are solutions, to this differential equations. Here's the differential equation. X squared y double prime plus 7 xy prime plus 13y is equal to 0. Okay. Time out for just a moment here. Okay. First, look at this differential equation. Remind ourselves, is that a linear differential equation?
Yes.
Yes, it is. The x functions here, they have nothing to do with linearity. It's only the y's. And you see y double prime shows up without any other y in that term. Y prime shows up without any other y in that term, and y shows up without any other y in that term. If there had been a y prime with that last y, or a y prime squared in that middle term or something like that, that wouldn't be linear, okay? Because you have more than one y expression in each term. The x's, the coefficient functions, they don't matter at all. So it is a linear second order, maximum derivative is 2, second order linear differential equations, and it's homogeneous because it's equal to 0. That's what homogeneous means in this case. Okay, so that's a linear second order differential equation. Now they claim these two functions are solutions to it. Back in chapter 1, I would have said, let's verify that. Frankly, I don't want to verify that. If you just think about this a little bit, those could be some pretty hairy things to calculate. Okay? But they say they're solutions for the differential equations on an interval, and this interval is 0 to positive infinity. Now, do you have any idea why they say that interval? Now, this is an interval of x. Okay? I want you to look up here at these two solutions. You have a log of x. You cannot take the log of a negative number or of 0. So therefore 0 cannot be included, and all the possibilities have to be positive. Now this doesn't guarantee this will work, but you sure couldn't have a bracket here, because 0 can't be included, and a negative 17 couldn't be included. No negative number could be included. So at least this is making sense for both of those. And the fact you have an x in the denominator, that means again that 0 can't be included. So at least the interval sort of makes sense. Now, we're going to take their word for it. These are solutions. Okay? I'll buy that without verifying. Okay? The one thing to note here, these coefficient functions, they are continuous everywhere on this interval, 0 to infinity. That's a polynomial, that's a polynomial, that's a polynomial. They're continuous everywhere, but specifically on that interval. If you had had a x squared over x minus 1, no, that would not have been continuous, because 1 would have made a 0 in your denominator. So when I said those coefficient functions, they're not bothering anything, that's because they're all polynomial. If they had been a rational function that would not have been continuous on that interval, then all bets are off. But these are, so you're fine. So that's all we have to do to worry with them. The other thing, of course, is that the first one is not 0 anywhere on that interval as well. Your a sub n cannot be 0. And as long as 0 is excluded there, that's fine too. So those two conditions are met. Okay? So let's consider the Wronskian. And the Wronskian of these two functions, the first one being cosine, and I'm sorry, my pen is not writing well. I did not write a straight line there, the pen did. Cosine of 2 log x over x cubed, comma, sine of 2 log x, stopped writing again, okay, over x cubed. Okay? Wronskian of that will be what? It's a determinant. Okay? You tell me what goes on the top row.
Sine.
Well, no, start with cosine.
Cosine.
Yeah, cosine, I can't write it. There it comes. Cosine of 2
log
x over x cubed sine of 2 log x over x cubed. Sorry, I'm writing so slow, but it's the only way the pen will write. Now, the bad news is we got to take the derivative of each of those. Okay? We only have to take one because you go to n minus 1 derivative, and since the equation's the second order, only have to do the first derivative. So, what kind of rule are we going to need for this one?
For this one, would product be okay?
Product rule would be okay if you rewrite them. So I like the product rule better. So I'm going to rewrite this. I'm going to write it slightly in a different order. X to the minus 3 times the cosine of 2 log x. And the second one would be x to the minus 3 of sine, or times sine of 2 log x. Okay, if you did them the way they are listed there, you would use quotient rule, but I prefer product rule. So how does product rule go?
It goes the derivative of the first.
Okay, derivative of the first would be?
The derivative of the first would be x. Oh, it's just negative 3. Yeah, negative 3x to the negative 4th.
Right, times the second, which is cosine of 2 log x. If I could get it right, there it comes. Okay, plus, only this one would be a minus. I can't get my pen or eraser to come up now. Okay, let's see if I get the pen to come back. There we go. Minus what?
Negative 3x.
Okay, no. You've already taken derivative of the first. So you write the first.
Minus x minus 3. I mean x.
Okay. It would have been a plus x to the minus 3, but I'll show you why I put the minus there. Because then you do the derivative of the second. What is the derivative of the second?
The derivative of the second would be 3.
Okay, the second, not the first. You already did the first. The second, that's the cosine function. What's the derivative of the cosine?
For the cosine 2 log, I'm having a hard time seeing it on my phone today. I don't know why.
Okay. What's the derivative of cosine?
Sine.
Minus sign. That's why the minus sign's there. Okay, so that's why I put the minus sign there. Sine of 2 log x. But then, with the chain rule, you have to take the derivative of the 2 log x. And what's the derivative of that?
The derivative of
2 log x, right.
Is it 1?
No, it'd be 2 over x.
2 over x.
Because the derivative of log x is 1 over x. So twice that is 2 over x. Okay. Now, if you go back and write what that gives you, I'm going to pull out the minus, okay, and then put my parentheses. And I'm going to put the 3, no, I'm not, I'm going to put the x to the 4th on the bottom in a minute. Cosine 2 log x, okay. I pulled out the minus, so that's going to be a plus, and I have a 2 there, this one over here, so that's going to be a 2 sine of 2 log x. Okay. Okay. And both of these are over, or the first one here is over x to the 4th, right? But this one has an x to the 3rd, but then you have another one, so that's over x to the 4th. Okay? You buy that so far? Okay. Now, I'm not sure it was wise to pull out the minus sign. I think not. So I think I'm going to put that back in again because it doesn't do me any good out there by itself. So this one, under the cosine, will be this one. Minus 3 cosine of 2 log x minus 2 sine of 2 log x. Obviously, I didn't leave enough room, did I? It's coming back. It's just slow. Ah, here we go. Okay. Over, because they both are over the same denominator, x to the 4th. Okay. Now, we got to do the same thing for the sine, take derivative of it. Like I said, I didn't leave enough room, so I'm going to cheat. This is so frustrating. Okay. I'm going to leave as much room as I can there. I can't get my pen back. There we go. All right. Now, let's take the derivative of this one. Okay? I'm going to do this in a different color so we don't get them confused. Is that okay? Yes. You pick a color. Blue?
Yeah, blue.
The Carolina or dark?
Dark.
Dark, okay. All right. So we're going to take the derivative of this one. Okay? And if we do it just like we did before, you like to do derivative of the first. Again, that would be a minus 3 x to the minus 4. And derivative of sine is positive cosine. Oh, wait, I'm sorry. You just write down sine. Okay, I'm sorry. The derivative of the first times the second, which, now, I'm sorry this is being so obstinate today. I mean, part of this are my little errors, like writing cosine when I meant to write sine. Okay. Sine of 2 log x. Okay. And then the second term is the first, which will be a minus. It would have been a plus, but you'll see why in a minute. X cubed, x to the minus 3, sorry. X to the minus 3 times the cosine. That's where the minus came from. Minus cosine of 2 log. It'll show up in a minute. X. Okay. And all that is over. There was an x to the 4th down here. Oh, I'm sorry. I skipped a space. Okay. Let me take off my division line there. I'm jumping the rabbit too soon. Okay. All right. That's what your derivative of the x to the minus 3 sine blah, blah, blah is. Okay. Rewriting that would be a minus 3 sine Wait, I messed up something here. Derivative of sine is positive cosine, not minus cosine. I was doing the previous one. Okay. The minus is here because that was the derivative of minus 3. Okay. Sine 2 log x. I'm writing it, but nothing is showing up here. Okay, there it showed up. Plus 2. Oh, I forgot to do the chain rule on this. I knew I forgot something. This is a 2 over x, same as before. Okay, so that's where that 2 came from. Cosine 2 log x. And that would have been over, okay, this one is over x to the 4th. And this one was over x to the 3rd, but another x gives you x to the 4th down here too. Okay. It takes a while, but it shows up. So if we write these two in there, this one, I'm going to keep it in blue now because that's the derivative that goes under here. Minus 3 sine of 2 log x plus 2 cosine of 2 log x over x to the 4th. Okay. Now we need to take the derivative of that thing. Not a derivative, a determinant of that thing. So what I think I'm going to do is and here's where they cheat like crazy. Okay? But I'm going to go along with them because I don't want to do it either. Okay? Okay. I'm trying to get my eraser to come up. Okay? So what I'm going to do is erase this stuff here. This is all the scratch work I was doing, you might say. I don't know why it won't erase. The whole thing is so stinking slow. All right. I have to erase it several times before it'll ever erase. Okay, down to 2 marks, and they're gone. All right. Now, if you tried to do a determinant of this, it would be this thing times that thing, ooh, boo, hiss, okay, minus this thing times that thing, another really big boo, hiss, okay. Really, they're not too bad because your denominators are both x to the 7th on both of those, so that's going to be okay. But your numerators are going to be pretty awful. This will be minus 3 cosine, that same argument, sine, that same argument, plus 2 cosine squared of that argument. And then when you do this one, you'll have minus a minus 3, so that would be plus 3 sine cosine. Well, that'll wipe out this one, and then you would have a minus times minus, which is plus 2 sine squared, that thing. Well, you have a 2 cosine squared and a 2 sine squared. Add together, that gives you just 2 over x to the 7th. Okay? I know I did that awfully fast, but do you buy that? when you multiply these two together, okay, that will give you, now your denominators are always going to be x to the 7th, okay? So I'm going to write that down. I think I'm going back to black here, if that's okay. It just shows up a little better. Multiplying this out of that gives you a minus 3 sine of that thing, I'm not going to write it all in, times cosine of that thing, okay? Right? Plus 2, I'm trying to wait for my pen. It's just going nuts on me here. Okay, it just clicked out of everything. And I don't know why. Don't tell me I'm going to have to, I'm not going to do all that again. But it went way back to the beginning. Okay. There we go. Thank goodness. Okay. So you got the first, this times this gives you minus 3 sine times cosine, plus 2 cosine squared of that thing. I'm not going to write it all in there, right? Okay. Then when you do this one, remember that's the negative. I can't get the line to draw. There it goes. Minus those. That will be, and everything's over x to the 7th. Okay? So minus this, well, that's the sine times a minus this, that's going to be a plus 3 sine that thing times cosine of that thing, right? And then you got, remember, it's minus because you're going this way, so minus times minus would be plus 2 sine squared of that thing. Okay. And all this is over x to the 7th. Okay. Now, the minus 3 sine cosine will cancel out the plus 3 sine cosine. And then what you have left here is 2, factor out the 2, cosine squared plus sine squared. I'm going to write them in different orders. Sine squared of this plus cosine squared of that same thing, right? And all this is over x to the 7th. Okay? Well, what's sine squared plus cosine squared? Remember trig class? That's 1. So you just get 2 over x to the 7th. Okay? That's it. There's your Wronskian. Guess what? That's never, ever, ever 0. It's always, and when your x's are all positive numbers, between 0 and positive infinity, that's positive. Okay? So you just got 2 over x to the 7th. That's never 0, and by the way, never negative either. But the main thing is never 0. So that tells you those two solutions here are linearly independent. And that's all that I wrote linearly independent. And it just will not write. Okay, there we have. That's what we're trying to show. Okay? So that's all that they asked for. Whew, goodness, that wasn't a hard problem. It was messy, but then the pen just made it even worse. All right, to erase? Okay. That leads to the definition 4.1.3. What which is a fundamental set of solutions. Okay? Any set, my pen is not writing at all. Okay. Any set y1, y2, y3, ... up to and including y sub n of n, all n of those are linearly independent, okay, solutions of the, if I start writing too fast, it loses it. Okay, of the homogeneous, goodness gracious, this pen is driving me nuts. It'll write some letters and won't write the others. Homogeneous, I'm going to leave it like that. Linear, I'll leave that like that. Nth order, I'll leave that like that if it'll write the D. Okay, nth order, differential equation, D, E, differential equation. Okay. On some interval I, okay, is said to be a fundamental set of solutions on that interval. Okay. A lot of blah, blah, blah words. Here's what that boils down to. Come on back. Come on back. There we go. All right. There we go. If you can find, okay, start out. You got a homogeneous, linear, nth order differential equation on some interval. Okay? If you can find, in its nth order, n solutions to it, and they turn out to be linearly independent of each other, in other words, the Wronskian of them is not zero. It doesn't matter what it is, positive, negative, doesn't matter, as long as it's not zero, then you have a fundamental set of solutions. Okay? But you have to have all those things met. It has to be a homogeneous, linear, nth order differential equation on some interval I. And if you can find n solutions that are linearly independent, stop right there, you have a fundamental set of solutions on that interval I. Okay? Now, the next theorem, I'm going to write underneath this, and here's what that says. That's supposed to be a THE, and it just jumped from one to the other. There exists, I can't get the E to write, the X half of it wrote, and then it wrote again, exists a fundamental, I'm going to shorten this, fundamental set of solutions for the homogeneous, again I'll abbreviate it, linear, again I'll abbreviate it, nth order, I'll abbreviate that, differential equation on any interval I, for which it's defined. Okay? There has to exist a fundamental set of solutions. There has to. If it's a linear, homogeneous, first order, an nth order set of differential equations, it's got to have a fundamental set of solutions. It's going to be n of them. There will always be n of them. They'll be linearly independent. Okay. Now, does that mean there's one and only one? No, that doesn't mean that. You can have those linearly independent solutions written in different ways. And remember, you can then make any linear combination of them, and there's another one, you know. So, but there will always exist a fundamental set of solutions, n of them, for that nth order differential equation. Okay. And it says, analogous to the fact that any vector in 3 dimensions can be expressed as a linear combination of linearly independent vectors I, j, and k, any solution of your nth order differential equation on the interval I can be expressed as a linear combination of this fundamental set, okay, this independent set of solutions, n of them. That's the basic building blocks for your general solution for your equation. And that leads to the next theorem, which I don't think I have room to write here, so I'll go to a clean page, okay? All right. How are we doing on time? Okay, I think about 10 minutes, 15? Okay, all right. Here is the next theorem, 4.1.5. Let, if my pen is quit writing again, except just occasionally, and then it writes over itself several times, let y1, y2, it just isn't writing. There was a y1. That is so convoluted you can't even read what it was supposed to be. Oh, part of the problem may be that my power connection is bad. I just happened to glance down at that. That's a little bit better. Let's see if that helps. Well, it started erasing better, but then it froze itself again. I talked with the dean this morning and said I need a new computer, and she said let's see what we can find. So I think it may be promising. It may not help any this term. By the way, are you graduating this term, or have you got another term to do this summer?
I'm graduating this term. They're trying to figure out how they want to do it. They gave us 3 options. They said we can either do an online one. We can try to do one. I think they said in July if like things open back up, or in June or July when things open back up, or do like one together in the fall.
Right. Yeah.
This summer, I'm not coming back for the fall, just for graduation.
Yeah, you're going to be transferred by then?
Mm-hmm.
Where do you think you're going?
So I've been accepted to Alabama A&M already. But now, with all of this craziness going on, I don't know.
Okay, where did you say initially? I couldn't hear.
Alabama A&M.
Oh, A&M, okay.
Yeah, I was trying to transfer.
Okay.
Like, transfer portals, and then use like 5 Theta Capital.
Right.
Use that to try to get that reference.
Right.
Now I've gotten myself to another lease with my apartment here because there's so much uncertainty, and I didn't have the money to move, so you can't really move right now anyway. So it's just like that. Timing was just kind of bad. So what I think I'm gonna end up doing is try to co-op.
Right.
All this craziness it's supposed to be for the fall, so that actually might work out perfect for me. My lease isn't until next year now, so that way I could kind of save up and find me a decent place to stay.
Right.
Yeah, got a lot to figure out now.
Right. You know, A&M had some sort of deal with Lawson about being able to take a bunch of their classes here. Have you looked into that?
Well, that's pretty much what I've been doing. I've been taking, like, that's why I took.
Oh, you've already been doing that. Okay.
Yeah, that's what I've been doing. Because I know that the curriculum as far as engineering is pretty much the same throughout the state. So,
Right.
you got to take the maths, you got to take the sciences. So that's what I've been doing.
Right. Okay. Well, that's here at Lawson, but I mean, I don't know what programs they have, but A&M was offering full degrees that you take here on.
I don't know if it was mechanical engineering though.
Yeah, I doubt if engineering would be on it because those labs are pretty intense, and I don't think they can move those down here.
Yeah, I was about to see if anything. I mean, maybe an AutoCAD class, but I took that as a freshman, but it's a Tuskegee. So,
Right.
but I did want to kind of brush up on that. So, but yeah, I don't think they had too many of my things. Because I remember when I first got to Lawson, they didn't really have like engineering, like mechanical engineering courses here. When I first got here, they may have them now, but at this point, I'm just go ahead and graduate.
Right.
I do still have to have a certain amount of classes that I take from that university, so
Right.
that way I didn't want to take too many classes at Lawson, and then I already had classes at Tuskegee, which those should transfer with no problem. Well, I think those should transfer with no problem, but I got to pay the application fee before I can see like what all that I would still need. They want to show it to you before you actually have officially applied. Like, even though I've already been accepted, I still got to do an application fee. So,
Right. I've been trying to write while you were talking. So I have been listening, though. I'm just trying to finish this thing so we can read it together. With it writing so poorly. Okay. This is so bizarre how it does. All right, here's that last theorem. The last one I think we'll have time for today. Let y1, y2, y3, and all the way up to y sub n be a fundamental set. That means these are all linearly independent of each other. Fundamental set of solutions for the homogeneous, linear, nth order differential equation on some interval I. Okay? N equations, nth order, you got them all. Fundamental set. Then the general solution, this is what we call the general solution of that set of equations on I, is y is equal to c1y1 plus c2y2 plus c3y3 plus ... all the way up to cnyn. You include every one of those fundamental set of solutions with some arbitrary set of constants, ci's. They could be anything. Some of them could be zeros, some of them may not be. It's whatever they happen to be, whatever you choose them to be, that will also be your general solution for that nth order differential equation. Okay? Now, a lot of blah, 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 and it almost sounds like the same thing we were doing before. It almost seems like we've gone a complete circle here, but really we are that's almost what we have done. And, of course, they go through the proof using a 2x2, which is the simplest ones, and then they do the determinant of that, which basically comes back out being Wronskian, but you know that's not equal to 0, so they actually do the proof here. Okay? So I'll let you read through that if you're interested. It's Not all that exciting, but it does prove it. I'm wondering now, do we have time for example 7? Let's 4 minutes. Let's see if we do. If not, we'll pick up with this next time. Okay, I think I'll go to a clean page. It just depends on how fast my pen will write. And right now everything's slow. Okay, here we go. Here's two functions. y1 is equal to e to the 3x. If the pen would write. Okay, e to the 3x, that's supposed to be a comma, y sub 2 is equal to e to the minus 3x. Okay, I don't know if that's going right. Yeah, there it did. Okay, and the claim is these are both solutions to or of the, it won't write, homogeneous, linear, second order equation y double prime minus 9y, it just won't write, is equal to 0. Now, in just a short time, we're going to have how in the world that we're going to come up with that solution. They're not having us do that yet. We'll get there in a little while. It won't be too long, as soon as we finish this section here. And this is true everywhere from minus infinity to infinity. All real numbers for x. Okay. That's your interval. Now, they say by inspection you can tell these are linearly independent. Well, if you think about it, e to the 3x does something like this, e to the minus 3x does something like that. There's no way one of those is a multiple of the other. Okay? So forget about it. Those are linearly independent. That's why they said by inspection you can see that. So we'll leave that off for now. However, if you don't want to do that, you can do the Wronskian. So maybe we should, because we haven't done but maybe one or two, and those are fairly difficult. This one shouldn't be as bad. The Wronskian of these two, I'm not going to write them again. What would be the top line? Okay, e to the 3x, e to the minus 3x. Those are the functions. Second line is the first derivative of that. What's the first derivative of e to the 3x?
E to the 3x, it would be 3x.
3 e to the 3x. And this one would be?
That one would be negative 3x e to the 3x.
To the minus 3x.
Minus 3x.
Okay. Do the Wronskian, you multiply those two together, and you get minus 3 e to the, well, minus 3 is all, because e to the 3x times e to the minus 3x is 1. Cancel out, absolutely. So that's just going to be a minus 3. And then you do the up diagonal, which is a minus, and that's going to be minus 3. So this is minus 6. And all it takes for that to be linearly independent is the Wronskian not to be 0. That's not 0. Minus 6 is perfectly fine. That is not 0 anywhere, okay, for any x in that domain. Not ever, okay? Now, and since these are linearly independent, they're both solutions to that differential equation, and that would be really easy to show. We just don't have time for it. Then we know the general solution would be y is equal to any C1 any real number c in the world, e to the 3x plus any c2, any other real number that, e to the minus 3x. Okay, that's your general solution. Okay, and every solution can be expressed as some linear combination of those two. Okay, I think we're completely out of time now, right?
Yes, sir.
Okay, so let me, before I close out, give you your homework exercises. And I guess Keiston never showed up, did he? I've never heard him come on. Okay. For some reason, you're not even showing up on my screen. I can hear you. That's why I know you're here. But we'll begin next time with example 8, top of page 127. So homework, we almost finished 4.1.2. We just have 4.1.3. Well, hopefully that will go a little faster. We'll see. Homework exercises here. Any of the odds that are in the back of the book, 1 or 3, 5 or 7, 9 or 11. No, 9 or 11. Okay. Then 13, that covers 4.1.1. 4.1.2 would be any of the odds 15 to 21 that are in the back of the book. Any of the odds 23 to 29 that are in the back of the book. We'll stop there and pick up with the 4.1.3 next time. We'll finally, hopefully, be through with 4.1. The rest of the section of this chapter will go much, 4.2 is a little bit of a problem, but it's a very short section. After that, they're actually pretty fun to do. This is just slugging through it, and that's what we're doing now. All right, any questions?
No, sir.
All right, well then we'll see you on Wednesday and try to get your stuff in, especially that research paper. You got everything else in, so we'll look forward to seeing you Wednesday. Okay. Yeah, you're stuck inside anyway, aren't you?